So let us start this session of memory design and test with a very quick review of what we did in the last class. So who will tell me what were we doing in the last class?
Sir, we were looking into the pre-decoder circuit, sir.
Okay, we looked at the pre-decoding. Okay.
It's a NAND and NOR based pre-decoding. And we saw how we'll be connecting them in 2 stages so that we can reduce the delay. And after that, we saw the performance analysis, like what happens if we use NAND and NOR exactly about the speed, PPA.
We also see the use of pages and banks.
We also looked at what a page means, what a bank means, and how they can help us in reducing delays. Okay, and how scrambling can change everything. You know that we reviewed in the last class again. Yes, and
static and dynamic decoder designs.
Static dynamic decoder designs. And
layouts.
How to organize the layout of a row decoder region, the post decoder region. We looked at the programmation aspects of it. So any inputs about programmation that you want to highlight?
Sir, I mean the row that is closest to the PMOS side should be or the driver
the
side.
proximity effect.
Yeah, proximity
effect. Yes. So what we did on one of the buses, for the first bus which was far away from the NWell, we said, okay, let the vias be placed in whichever manner. The transistors were also placed in a particular manner, no issues. Whereas for the second one, which was close to the NWell, we said, okay, we will place all the transistors in one column so that each of the transistor is equidistant from the NWell. And then we just changed the programmation, and that meant a little extra capacitance probably on the metal line there, but overall we saw a benefit. And we also saw that by doing it like this, we could also reduce the total number of tappings to offset the extra horizontal metal that was being targeted there. Okay. So today we will start to look at mismatch. Yes, Faisal?
Sir, I have a question. Sir, when you gave the example of 10 address bits and we were using 4 input NAND gate in the post decoder. So how this 4 input NAND gate is fixing the 4 stages of pre-decoder? I was not able to get this part.
So how many inputs would you need in the post decoder so that your pre-decoding logic can fit into it, can all be connected into the post decoder? आपके पास 10 एड्रेस बिट्स हैं?
Yes sir.
आपने 10 एड्रेस बिट्स को प्री डिकोडर्स के अंदर डिस्ट्रीब्यूट करा?
Yes sir.
प्री डिकोडर्स कुछ आउटपुट्स देंगे?
Yes sir.
Output of every pre decoder has to be connected to the post decoder.
Yes sir.
If any of the pre decoder is missed, then the decoding will not be complete.
Yes sir. Yes sir.
So if there are 4 inputs, then how many pre decoders can be there?
If there are 4 inputs, then
if there are 4 inputs at the post decoder stage, at the post decoder NAND, there are 4 inputs. So how many pre decoders can be there at most?
Is it 2 to the power 4? No. So I am confused in like
how many number of pre decoders can you keep?
4, like 4 को satisfy करने के लिए 4 तो चाहिए.
बस
हम स्टेजेस की बात क्यों कर रहे थे वहां पे कि हाँ हमने एक 3:8 मार्क्स यहाँ पे लगाया, फिर उसके बाद जो किसी ने बोला था कि हम 5 2 to 4 डिकोडर यूज कर लेंगे.
हाँ, तो चलो 5 2 to 4 डिकोडर यूज करें तो कितने इनपुट आ जाएंगे पोस्ट डिकोडिंग पे?
अच्छा, तो वो 5 हो जाएंगे, इसलिए हम ओके इसीलिए ओके ठीक है अंडरस्टूड. थैंक यू.
ओके राघव
सर, वो पोस्ट डिकोडिंग में आपके लिए स्लाइड में वो सेटअप टाइम का मेंशन किया था, तो सेटअप टाइम उस कंसेप्ट का यहाँ पे क्या वैलिडेशन, मतलब वो समझ में नहीं आ रहा था, लाइक कैसे रिलेट करना है उसको यहाँ पे।
What is setup
मतलब
time? What is setup time of a flock, let us say, of any sequential element? What is the setup time of a sequential element? How would you define it?
so the time before the time before the sampling edge that the data should become stable.
So time before the sampling edge where the data should become stable. Sampling edge of clock. इसका
Sampling
मतलब
of
wherever clock and data are mixing, there could be a definition of setup time, and wherever there is a latch which is clogged, there could be a definition of hold time. Is this clear?
so where latch is clock.
Hold time छोड़ दो. Setup time की definition, wherever a clock is mixing, there is a setup time. Is this clear?
Yes sir, yes sir.
तो post decoding में clock mix होती है.
सर होनी तो चाहिए।
हाँ, है ना? तभी तो वर्ड लाइन आएगी और वर्ड लाइन को कंट्रोल करोगे आप. नहीं तो स्टैटिक में आती रहेगी वर्ड लाइन, है ना?
ओके
नहीं तो
सर।
आपने इनपुट चेंज करा, वर्ड लाइन चेंज हो गई. ये तो अलाउड नहीं है.
यस सर।
Word line should come only when you're in an active cycle. It cannot come when there is no clock. So clock has to be mixed in the post decoding stage. So clock and decoded address are mixing at the post decoder.
क्लॉक एंड डिकोडेड एड्रेस। सही, डिकोडेड मतलब पोस्ट डिकोडर के बाद की डिकोडिंग जो मिला वो बोल रहे हैं आप?
Pre decoded भी.
ओके।
Those signals address inputs are partially decoded, and that is when they are mixing at the post decoder. Then in the post decoder the clock also mixes with this decoded address. Only when the clock comes, complete decoding happens. Otherwise the decoding will not complete.
Yes sir.
In another design you could say, okay, decoding is completed, I also know which word line needs to be selected. When the clock comes, I will select the word line. That is also a possibility. That is also fine. Whatever it is, whichever way you do, whether you halt post decoding until clock arrives, or you simply halt word line generation until clock arrives, whatever you do, we realize there is a mixing of clock and some semblance of address decoding that is happening in the post decoder.
Yes sir.
So there is clearly a setup time that can be defined there.
तो सर जैसे कि जो आपका हमने स्टार्टिंग स्लाइड्स में देखा था, जो आईओ सर्किट जो हमारा कंट्रोल रीजन होता है वहां पे क्लॉक जाती है क्लॉक जनरेटर में, देन इट इज गोइंग डायरेक्टली टू द पोस्ट डिकोडिंग स्टेज। तो हमारा
Directly.
नहीं सर, क्लॉक जनरेटर के बाद मतलब इट इज गोइंग थ्रू। सो प्री डिकोडिंग में तो क्लॉक नहीं दिखाई थी उसके हिसाब से।
नहीं, you could have a dynamic pre-decoding stage, तो वहां पे भी clock हो जाएगी. You are a designer. You can choose whatever.
ओके। तो सर जैसे कि हमारे पास जो डायग्राम था पोस्ट डिकोडिंग का, नैंड के बाद जो हमारी लाइन सेलेक्ट हो रही थी, सो वी कैन से कि जो लाइन सेलेक्ट हुई आफ्टर द नैंड डिकोडिंग, उसके बीच में और क्लॉक के बीच में एक सॉर्ट ऑफ एक सेटअप का कंडीशन आ जाती है।
Basically, you want that as soon as the clock arrives, at that post-decoding stage, my inputs must have been stable, and I should right away drive the word line.
ओके। और सर
So
ये जो
there
डिले
comes the
होगा,
definition of setup time.
और सर ये जो डिले होगा सेटअप का, ये आपका डिपेंड करेगा जो आपका नैंड डिकोडिंग का डिले है, तो उसकी साइजिंग उस
The
सबसे।
setup time is dependent on two delays. First is NAND decoding delay, address decoding
यस
delay.
सर।
Second is clock propagation delay. Clock को भी तो delay होगा ना. You cannot say कि clock जो external clock का rising edge है उसके साथ आप compare करोगे word line वाले delay को.
यस सर।
है ना?
सर बट एज अ डिजाइनर हमारे पास तो केवल डिकोडिंग वाला ही डिले मतलब कंट्रोल कर सकते हैं, राइट?
Clock का control, clock generation तो तुम्ही ने करा ना, internal clock generation.
ओके, बफर्स यूज करके।
You buffered the clock into the row decoder region ना.
यस सर। नहीं।
You have control over everything inside the memory there.
ठीक है सर। ओके।
Yeah. Faisal?
सर एक चीज क्लैरिफाई करना थी कि यू सेड फाइनल ड्राइवर जो है हमारा शुड बी हाई वीटी
Of the word line.
हाँ, ऑफ अ वर्ड लाइन, क्योंकि इट हैज बीन मेड बिग टू ड्राइव बिगर लोड, और हाई वीटी इसलिए क्योंकि लीकेज कम होगा. ओके ओके, बस यही था. थैंक यू.
Okay. So today we will enter into discussing mismatch, which is one of the most important aspects when we talk about SRAM design. Okay, any SRAM or DRAM or even flash NVM जो भी, तो memory design के context में mismatch का understanding बहुत बहुत important है, and that is what we will discuss today. But before we enter there, let me also share with you this set of projects that are being defined for you guys. Sorry. So the projects that are being defined for you guys, let me just share that also with you. So, okay, what we will do as a entire class, we will be designing a set of memory instances which would be sized 8192 words, 16 bits per word, and we will design it in mux 32 bits, mux 16 configuration. Okay, so let us quickly do some number crunching. How many rows are we talking about? Quickly.
512.
5 and 2. How many columns?
512.
5 and 2. How many address bits would you use for row decoding?
9.
9.
9. How many address bits do you have in total? 8K. 8K वर्ड्स है ना, 1K वर्ड्स के लिए कितनी होती हैं एड्रेस बिट्स?
10.
8K के लिए कितनी होंगी?
13.
13. तो how many address bits are going to decoder, column decoder?
4.
Does this match with the requirement of mux 16? To decode mux 16 we need 4.
Yes.
This is the memory instance that we will design as a class. Okay, we will design not just one memory instance, actually we will design a single port, that is one read write. We will design a register file, that is one read one write port, and we will also design pure dual port, 2 read write. Okay, is this clear till here? So अब आप लोगों के लिए जो projects हैं, the projects the way they have been defined is, some of the teams will work on the memory cell, some of the teams will work on the row decoders, someone will work on say column decoder, someone will work on write driver, someone will work on what do you say, sense amplifier, and so on. At the end of it, through this library that you guys design, we should be able to generate 3 kinds of memories: single port, register file, and dual port. Is that okay? So the TAs will open up the project sheet for you to register. Is any of the TAs here in the class, Abhi? Okay, they're not here. So they will open up the Google sheet where your teams can register. And though I know you guys have formed teams and everything, I would say please do not get stuck with your team and everything like that. If you are interested in working on say replica decoder design or replica array design or something like that, you can just see who others are interested and you can put your name there. Okay, you can decide to continue with the teams that you have already formed, 3 members each, or you can do it slightly differently and choose to work where you are interested to work. Is that fine? Any
Yes.
questions? Anyone who is not yet able to form a team or something like that? Anyone facing such a constraint yet? Okay, great. So yeah, there's a question.
So we'll be designing three kind of memory, complete memories, like one with array in which we're having one bit cell of like single port and one RF and dual port.
As a class, yes.
Three kind of memories we were designing. So
As a class, yes. Not as a
okay,
team.
sir. Okay, sir.
Okay. So for example, for sense amplifiers, there is a team that will be designing a single-ended sense amplifier. There's a team that is designing a differential sense amplifier. There is another team that is designing another kind of a sense amplifier. So there are three memories, but each one of you will be working in some team. So that is just one memory. When you make the layouts of a single-ended sense amplifier, you know that this is to go into the RF register file. Okay. When you do latch type sense amplifier, let us say you put it in the dual port. The other one you put it in the single port. So that is fine. That we will do. Okay. So now, so you will see the details in the sheet that will be released today, and you can register your teams there, and you can start to work on that.
So
Yes.
we will have to register. The register will also be open today only. Like
Yeah. Let the TS come back to you with the details.
okay.
Okay. You want more time? So from what I have understood, so what we will do is we will open the sheets to you for review. We will open them for registration later. ताकि आप लोग अपनी teams में discuss कर लें. If you need to reform your teams, you can do that. Is that okay?
Yes, sir.
So we will do it like that. So now we enter into this discussion on mismatch. What is mismatch? I assume all of you know at least this. What is mismatch?
Due to process variations during the fabrication, there will be a mismatch between two different cells in the memory, or it can be even in the IOs.
Any two devices, even if they are designed to be of the same size in terms of W by L, everything, even then, just by the virtue of the fabrication process being a normal process, there will be some mismatches between devices. This can appear as a variation in cell current. This can appear as a variation in leakage. This can appear as a variation in for SRAM cell in terms of static noise margin or write margin and so on. The impact of variation on static noise margin and write margin, we looked at it in much detail when we were designing the memory cell. Am I right? So today, what we are going to look at is, we saw that there is such a huge impact that can happen, but why does it happen? What are the sources of mismatch? And then as a designer, why is this discussion important? Because if you understand what are the sources of mismatch, you can then attempt to manage this mismatch in one way or another. So what we will be doing now is we will be reviewing the material. So I will be reviewing some parts, some slides of a tutorial that was given way back in 2006 in Design Automation Conference in DAC 2006. It was given by Synopsys, and it's a very, very exhaustive tutorial. The slides are available online. I will also share the slides with all of you on Classroom. But I want to cover a few of those slides which are very important for memory design, for memory designers in the class. So that is what we will be doing now. Is that okay? So you will get the access to full tutorial. I expect you to study the entire tutorial, but I'm in the class. I will go through the most important aspects of sources of mismatch. Is that okay?
Yes, sir.
So this is what I said. It's a tutorial from DAC 2006 by Synopsys. So when we talk of mismatch or when we talk of variations, we need to understand that there are two primary kinds of variations: random and systematic. So what are random variations? Random variations are variations which are intrinsic in nature. They are kind of global variations. They will appear whatever you may do. Whatever you may do, those intrinsic variations will appear. Process variations, again, the global variations, or for example, we discussed about it, because of which we get SF lot or SS lot or TT lot. Gate oxide thickness, the entire wafer, the gate oxide thickness is different, is a little higher, is a little lesser. That will mean that this is a global effect. And then there are pseudo variations which are event dependent. That is, for example, there could be dynamic IR drop, or there could be a temperature gradient in a chip, due to which these variations can happen. Okay. Systematic variations are something like WPE that we discussed. We discussed WPE in the last class. So systematic variations are those kind of variations. Systematic variations are also these kind of variations where you can, basically the difference between random and systematic is that for systematic variations, you can model them. Model them means you can reasonably accurately model them, and then you can simulate and see the impact of them on your exact device. Random variations, you can only statistically model them, and you can see the statistical impact only. You cannot really see the exact impact of random variations. Okay, so that is where we say that over here we have put in this concept of we can model these variations and see what impact they can bring about. Okay, this, for example, is an example of systematic variation. You made a layout like this. You know what your process is, in the sense what are your resolution enhancement techniques that you are using in your system. Since you are aware of those resolution enhancement techniques, you can already make a simulator and find out that, okay, my gate region would actually be like this instead of this. Okay, so what do you do now to improve the situation, to correct the situation? You can relax the design rules. You can say that, okay, these two structures cannot be so close together. We have to increase the spacing between these two structures, and so on. As you would do that, you will see that your design becomes more and more aligned to what you wanted it to be. Now this, for example, is a simulation of the polylines when you draw them like this. And these circles have been put there to identify and tell you those places where there is a lack of fidelity, where there is some challenge. And you see, there are issues like necking, there are issues like line end pullback, there are issues like non-matching transistor gates, and so on. So, for example, over here, it appears that these two gates were meant to be matched. They share the same active area, but look at the right side. The image on the right side shows that they have different length finally. Are you able to see this? The length here and the length here is different. Are you able to see this?
So length, I mean, of the right gate, it is bigger, right? Because it is extended to the other diffusion also.
So we are looking at the gate region. We are looking at only the gate region, not outside the gate region, only above the diffusion layer. So in this case, the diffusion layer would be something like this. If I just draw it, it would be something like this. And you see that the that the length of these two devices is different in this region. It has also been circled there.
The thickness, sir. The thickness, sir.
The thickness of the poly, which means length of the device.
Yes. Okay. Okay. Yes, sir. Yeah.
है ना? The thickness of the poly means length of the device. Na?
Yes, sir. Yes.
So it is different. So it means these two devices, which are supposed to have the same length and same width, would now actually have different characteristics. Am I right?
So can you please repeat the statement?
So these two devices that are marked with an arrow on the left side, they have same width and same length.
Yes, sir.
Now look at the right side. Due to various effects like line pullback, due to necking, due to whatever, so many different, because the polys have been designed in such a way that they have different poly to active spacing, they have different contact pads, they have so many differences amongst them.
Yes.
Are you able to see this? So
Yes,
what
sir.
is fabricated finally, on that OD that will be drawn, you will see that the width of the poly, that is the length of the device, is going to be different.
Okay. Yes.
And this is not a random variation. When you made this layout, I can anticipate that this is going to happen. Are you able to see this? This is not a random variation. When you make the layout, you can tell that this is going to happen.
Sir, actually, I had to ask one thing, sir, कि जो right side वाली जो आप दिखा रहे हैं, that is a simulation of this left side layout, kind
Yes,
of.
that's a
Is it
simulation of how the poly would finally turn out.
okay? So even before manufacturing, able to see this kind of.
You can, yes. Even before manufacturing, there are simulators that can model your resolution enhancement techniques, that can model your process, and that can give you this kind of a view.
Okay. So, but I'm not able to understand like how it is different, because in intrinsic you said that in random we have intrinsic and pseudo. The,
ये
what
random नहीं
exactly?
है. These are systematic variations.
So, but in random में वो क्या थे sir, मतलब?
एक minute. These are systematic variations. Let us first get this right. Is that clear?
Okay.
These are systematic variations. So don't confuse them with random. I'm not started with random yet.
Okay.
So these are random because you can model them, or
These are systematic because we can model them.
This is systematic because we can model them.
Yes. We can model them exactly. I can tell you that left device will have a faster or more current than the right device. Whatever. Because I can always say this through this modeling simulation that I did. These are systematic variations. Random variations would be, for example, as we will look at in the next few slides, doping variations. There could be more dopant atoms in under one gate than the other. And that is what is random. You cannot model it. You cannot say that everything else is matched. Even then, device 1 will be faster than device 2. In some samples, device 1 will be faster. In some samples, device 2 will be faster. But with systematic variation, just like well proximity effect, you can say, oh, this device is close to the N well, so this is going to be slower. Is it not? So these are systematic variations. Okay.
So one doubt.
Mm-hmm.
In the sir, you said that was the simulation of the layout. So sir, the information obtained about that necking or whatever effects, these are provided on the basis of experience by the foundry, right?
And optics simulations, Deepa.
Yeah. Okay. Okay.
Finally,
Okay.
it is all optics. You know which wavelength is to be used. You know the material. You know everything. You have to model it.
But sir, you said that I know exactly if the right one or the left one would have the narrower length. So that kind of prediction, I was just wondering how it can be, explained logically. I was not able to understand why would
So
how
let us
can
look
we?
at it. Yeah, let us look at that layout. In this layout, do you see that the spacing between poly and active is changing?
Sir, left one.
Yeah, in the layout, left one, you see the spacing between poly and active is changing?
Yes, sir. You can see that.
Huh? So what does that mean? That when finally the device will be made, there will be bending. The bending of poly will happen earlier for the left device and later for the right device.
Right. Right, sir. Right.
Okay.
Okay.
Then you see that the poly pad, the contact pad is closer to the in the left device than the right device. So you see there are so many things
Yes.
that are evident in the layout itself.
Yes. 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 Yes.
When you run the optic simulation, it will give you that. It would say that okay, the necking will happen here,
Mhm.
rounding off will happen here, line pullback will happen here.
Yes.
Okay.
Got it. Got it.
The differences are evident. And to avoid these differences, you make structurally matched layouts. When you will design your sense amplifiers, whichever teams work on sense amplifiers, you will be expected to do common centroid layouts with structural matching even on the metal lines, not
Yes.
just on devices.
Yes, sir.
Okay, so that such impacts, systematic variations are completely done away with. There is no systematic offset in your sense amplifier. Even
Yes,
if it
sir.
takes a little extra area, we will do it. Okay.
Yeah. Yes, sir. Yes. Got it. Got it.
Then the next kind of effects, again, systematic effects, is proximity. If there are devices which are placed far apart, there is more spacing between devices versus devices which are placed close together, you will see that the kind of stress that appears in the diffusion region, in the region where you have your contacts and everything present there, it changes. Look at the contours in the bottom graphs. The stress changes, due to which the PMOSs and NMOSs start to behave differently. In fact, it was said that 28 there is the P by N ratio changes by 28%. The mobility of the NMOS and the PMOS, the ratio changes by 28%. That huge an impact can happen.
So which stress are you talking about here, sir?
Stress. Okay, so let us say this is a device. There will be shallow trench implants over here on the side. So as soon as these shallow trench implants come into picture, what happens? The crystal lattice, the crystal lattice is broken. When the crystal lattice breaks, there are bonds which are dangling. There are bonds which now see a different kind of stress. That stress gets, as you can see in the contours, that stress gets transmitted to the gate region also. Are you able to see this?
So I mean, shallow trench implant able to get, but what is causing stress actually? I mean,
The breaking of the bonds, the breaking of the lattice structure of the silicon.
so due to the STI, shallow trench implant.
Yeah.
So the
See,
process
otherwise
of
this was all silicon. Otherwise this was meant to be all silicon. This was meant to be complete lattice of silicon. Is it not? You broke it with STI here and there, due to which devices now have stress. And the stress is different when there is a sparse device, sparsely placed devices, and it is very different when they are densely placed devices. Because STI can absorb some part of mechanical stress, it will not absorb all the mechanical stress. Or when there is a lot of STI, it gives a different kind of stress versus when there is a little bit of STI there. Okay.
So sir, like when we have the dense layout, so I can think of ki STI, the width will be less. I mean, the shallow time will be smaller. So that will lead to different kind of stress. I mean, the physical. Okay.
Yeah. So you design the layout, तो आपको दिखेगा ना कि यहाँ पे STI कम है कि ज्यादा है ना? And look at this. This is the result of the final simulation in terms of ring oscillator. The dense ring oscillator operates at a higher frequency than the sparse one. Overall, we saw that there is more than 10% timing variations just because of this effect.
So it means that stresses changes the device characteristics itself, I mean.
Yes, mobility changes, na? If there is stress in the silicon lattice, the way the electrons will move around will change. When you are under stress, does your performance change?
Yes, sir.
Exactly the same way, the transistor performance also changes. Ranjit?
Sir, what exactly is this STI, sir? I'm unable to understand this.
Shallow trench implant. We discussed about shallow trench implant in the second lecture of DVD, manufacturing process. How do you separate two devices from one another? You remember we said we would break open we will make shallow trenches between two devices and we would deposit. So before shallow trench implant technology, we would grow silicon dioxide on silicon itself. That led to that beaking effect. Remember? Between two devices, there would be a beak that would form, and there was a minimum DRC that was supposed to be maintained. We said, okay, we do not want to go with this beaking etc. wala funda. We will open up. We will open up the silicon and deposit oxide in there so that we can have denser layouts. We will not depend on growth because that would mean beaking would happen. That would mean more spacing between devices. So for density, we went for shallow trench implants, where the silicon is broken open between two active regions. We deposit silicon dioxide.
Okay, sir.
Okay. So that is the impact of device variation. So see, at that point of time, some of you might have felt why we are discussing all this manufacturing steps. It is very important because as a designer, you need to understand what all effects those manufacturing steps could have on your design. Okay. So similarly, we already discussed the dishing in wires. You remember that? The dishing phenomena in wires, because when we do chemomechanical planarization.
Yes, sir.
So how do we avoid this?
Sir,
Adding some
SiO2 in between.
We add some pillars of SiO2 in between so that the dishing doesn't happen. We make some slots inside wide wires. Ranjit?
Sorry, sir, I forgot. No.
Okay. So we add slots inside these wires so that those slots act as pillars and dishing doesn't happen. So this is again one of the systematic variations. You see a wide wire, you know that, okay, there is going to be some loss. You see sparse density of wire, you say, okay, there is expected to be some loss. So why is it important in terms of memories? Where do you have wires running around?
Array.
In the memory array, there are word lines, there are bit lines. So there is a huge density of wires. If suppose I say that I want to track my word line capacitance with a word line capacitance and resistance with a signal in the IO region, is there such a requirement? Is there a requirement to match word line with some signals in the IO?
No, sir.
No? Why?
So can you repeat the question?
Is there a requirement to match the RC of word line with some other signals in the IO region?
Yes, sir. I think if
recharge.
Yeah, we talked about the race conditions in the IO. That was the last slide we discussed. We saw that in the IO, the precharge should come before word line. We saw about this condition, the race condition. What does this mean? That the RC of precharge signal should be similar to that of, or at least there has to be some semblance of some relationship, deterministic relationship between RC of word line and RC of the precharge signal. So if, for example, now you in the IO region, you make precharge line as a single line running, with 1 micron distance spacing to any other line, will it behave the same as word line? Will it behave the same as word line? Hello?
Sir, the precharge line, in the sense you mean like the clock that is going to the precharge circuit in the
The
sense
metal
amplifier.
that you route, to connect the gates. Finally, you will route metals, na?
Yes, yes.
So that metal is very sparsely placed. There is no other metal wire within 1 micron of it. That versus the word lines in the array region. Will you say that these two lines are matched?
So I mean, I'm looking at how the wires are placed, the surrounding of the wires basically.
Yes.
So, but okay.
The word lines are spaced.
Because if the wires are dense, if the wires are densely placed, there will be lesser dishing. If the wires are sparsely placed, there will be more dishing. Or vice versa. Basically, softness of copper is different from the softness of silicon dioxide. So if there are more wires, it means there is more copper in that region. The CMP process will polish it in one particular way. If there are lesser wires, it means there is a different level of hardness in that region. The CMP process will polish it in a different way. And your wires and delays may not be matched. You wanted to match the delays, na? But the wires have different RC now. The delays are not matched.
So just because the different surroundings,
Yes.
we can have different RCs.
Yes. You see, that is and this is a systematic variation. This is what we mean by structural matching. That the structure of the layout in terms of density and everything should be matched. The bends that you see in the for one device should be similarly made for the second device also. Everything. Ranjit?
Sir, if the wires are placed denser to each other, then the chemomechanical process cannot polish out, the dishing cannot happen for the densely placed wires.
Yes.
But
so those wires will have lesser resistance.
So
Yes.
what does dishing mean, sir? I'm not.
So dishing means that CMP, during the CMP process, as you see in this right side figure there, when there are wide wires, they end up eroding, eating away the copper more than what was desired. Because copper is much softer than silicon dioxide.
So, sir,
So
the
CMP process polishes it more.
So, sir, it happens when the wire is not dense.
When the wire is, what do you say? When there is a lot of wire, lot of copper, because copper is soft, dishing will happen.
Sir,
Okay.
where did density come into picture, sir? Exactly. I didn't, because the according to what I understand is that it totally depends on the width, right?
Dishing depends on the width, but we are talking about another effect, erosion over here or field loss over here. See, look at the slides. There are two new terms which have been introduced, field loss and erosion.
Okay, sir.
So when there are so many wires, overall softness of that region is lesser than places where there are no wires.
Okay.
So more erosion will happen.
Sir, but suppose if we consider the case of denser wires, sir, the dishing will be less, but intrametal capacitance will increase now, sir. So that time RC also increases.
We don't know. Resistance is lesser. Because the wires are taller, the resistance is lesser now.
But C capacitance increases.
Yeah, C may increase. Now, do you realize that if R and C values move differently, they're moving differently now, is it not?
Yes, sir.
R reduced by 20%, C increased by 10%.
Yes.
RC would move in a different direction.
Yes.
Anything, whatever it is, the two wires, word line and pre-charge line, are not matched if they do not have similar density of wires around them.
Yes, yes, sir. Absolutely.
That is the point that needs to be established. Okay, Raghav?
So what do you mean by the field loss here, sir?
The field oxide, SiO2 loss. When you do CMP, the field oxide will also get polished, na? Okay.
And what is erosion, sir? Here.
Erosion means in between the wires. So field losses in those regions where there is not much density. So you see, in that is exactly what I was mentioning about. You know, when there is not much wire density, the height would reduce by only this much. But where the wires are denser, the height would reduce by a larger amount, and therefore your wires will be thinner, less tall.
Okay.
Okay. So that was where we talked about metal slotting earlier. And now today I'm introducing this term, which is called as dummy fills to you. Okay. So dummy fills are also done so that you have similar level of density at all places. However, inside the memory, you do not allow any dummy fills. Inside the memory, you want, as a designer, everything to be under your control, is it not? As a designer, you want the memory to behave exactly the way you want it. Right? So inside the memory, dummy fills are not allowed. But outside the memory, that is in the standard cell logic region, dummy fills are done so that dishing and erosion and field loss does not happen. Or whatever happens is systematically similar across all wires and all regions in the chip. Is that okay?
So like in the previous example, we were having different kind of spacing in the IO and the array region. So, and why I am calling that structural because I'm able to see the effects of that deterministically, how many delay variation. But what I'm doing to basically mitigate that if I'm having that?
We add extra metals. So these blue ones are extra metals which are simply added so that density of metals in all regions is similar. This is called as dummy fill process.
So these
You
are
do it in
metals.
the CAD layer itself. Yes, the blue ones are also metals, but they are not connected to any signal. They are floating metals. Now, what does this mean? If you allow this in the memory, what would happen? I said that we do not allow dummy fills inside the memory. Why? What would happen?
Area loss. Area
No,
loss.
there's no area loss. ये तो जहाँ पे layout बना हुआ है उसी के ऊपर add हो रहा है रंजित.
Sir, but
So
wiring
metal length would increase if we add them inside the memory, and it can also interfere with the other wires by coupling capacitance.
Yeah, see, you designed your IO region, for example, and you extracted that. You did all your verifications with that IO. Is it not? You said, okay, this IO will be repeated 10 times, 20 times, 50 times, depending on number of bits. You estimated the RC of the signal, and then you would do verifications. Then you would characterize setup time, hold time, everything. Now, to add the stage of going on silicon, the system says, oh, there is sparsity of metal 3 there. Let me add dummies of metal 3. So above your IO now, there are dummies of metal 3. What happens? The capacitances of underlying metal 2 would change. The capacitances of other metal 3 lines in that region would also change. So finally, what will be fabricated on silicon will have a very different RC than what you characterized, what you validated, what you designed your circuit with. Can you afford this variation?
So, but I can include this capacitance in my extraction itself. Can't I do that?
So the dummy fill stage is at the fag end. Just before you enter the fab, dummies are filled at that time. Dummies are added to the layout at the last stage, bilkul last stage before fab out, before fab in, let us say.
So, sir, they will be part of my GDS,
but you have not characterized them.
Okay.
They
So
will
I'm not
finally
able to
become a part
understand.
of your GDS. They will finally become a part of your GDS. But when you designed, you did not know that they will come there. So you did not put them. So the capacitances with which you designed were way lesser than what finally are there. Your system will completely go for a toss.
Sir, actually my doubt is having, because once we have done the layout, then we do the parasector extraction, right?
Hmm.
And so if we are, and GDS also is a layout file
Hmm.
only. So sir,
Hmm.
if I've done the layout and at the layout stage I am adding this kind of this dummy fills, then why can't I characterize them?
So as I said, the dummy fills are added at chip level. So you made the layout of a memory. A SOC designer designed the entire chip around it. After everything was done and the chip was being sent for fab out, at that time they felt that, oh, there needs to be 20% more metal 3 so that density is consistent. That is when they added these dummy fills. Now what will you do?
Okay. A SOC level designer is adding this basically. That's why I'm.
Even that designer is not adding. The tool will add.
Yes, sir.
Okay, so you cannot model them. You have to put a layer there which says no dummy, no tiling there, no dummy filling there. Above the memory, you have to put that kind of a layer. Which means there will be some additional DRCs that the memory designer, memory layout designer will have to take care of. We will take care of them. But we cannot accept uncertainty. Okay?
Yes, sir.
So slotting we already discussed earlier, that we make small slots inside wide wires so that there are kind of pillars of silicon dioxide in between, which prevent dishing. Okay.
So one more thing. So signal lines are same as the dummy fill. I mean, the concept is similar.
Signal line is like pre-charge, word line.
Okay. Okay. Oh, yeah.
Signal lines are what you designed.
Okay. Okay. Okay, sir. Got it.
Dummy fills got added later.
Okay.
Okay. Now we enter into the zone of random mismatch. Now look at this image. On the left side is one cross-section view of a transistor, and on the right side is the dopant profile, which is particularized. Okay. The red ones are donors, the blue ones are acceptors. Okay. Now what happens? Let us say you scale down. You scale down the technology and you expected 20. So this was your gate region. So this was your gate region. And you expected 20 dopants over here beneath the gate. Okay? But in reality, just give me a minute. In reality, there were, let us say, 3 extra dopants. All of a sudden, what happens? The contours, the potential contours of this gate device will be different from the device that you had designed it to be. You will now need more band bending. Are you able to see this? To get to the VT of the device, you will need more band bending, and therefore you may end up as a high VT device. A VT is slightly higher than the regular device that you had intended it to be. It can also happen that instead of 20, there are 18 dopants. Now, less band bending is required for VT to be there, and therefore you will see that the device is a little fast. Are you with me?
So, sir, this is random.
This is random. Two adjacent devices, structurally matched, WP is same, stress is same, everything else is same. Even then, you cannot control how many dopants will be there beneath your gate. It is physically not possible. So such variations, which you cannot really model deterministically, you model them statistically. You say that, okay, of 100 devices, 70 devices would have 20 dopants only. Now 10 devices will have 22 dopants. 10 devices would have 18 dopants. Then remaining 5 devices would have 25 dopants. And another 5 devices would have 15 dopants. And you say that there is a distribution. There is a distribution where some devices are faster, some devices are slower. Are you able to see this?
Sir, I have two questions. So one is why this process, why is this random, sir? I mean,
You tell me.
sir,
I want to bombard 20 dopants in a region which is, let us say, 1 micron by 65 nanometers.
so 1 micron by
1 micron device with
okay.
minimum length.
Yes.
So 65 nanometer into 1 micron. In that region, I want to bombard 20 dopants. Can I bombard 20 dopants exactly? Or sometimes there will be 21, sometimes there will be 19. It's a process, no? It's a natural process.
Yes, sir.
You're not
It's
placing dopants one by one. You're just bombarding and you're letting them diffuse. There are bound to be variations.
So, but the machinery which I'm bombarding, I have the frequency, everything I have in control, right? So I can be sure how much I'm
So you
bombarding.
have, so okay, let us do this experiment again, Raghav. You have a pencil with you? Pen, paper, pencil with you? Something like that?
Yes, sir.
You have control over your hand?
Mm.
It is the same pencil that I want you to write your name with 20 times. And it has to be exactly the same.
Yes, sir. Okay.
Can it be exactly the same?
No, sir.
No. Why?
Perfect is not there. Perfection cannot be 100%
It is a natural process.
Yeah.
It is a natural process. There are bound to be some variations. The velocity of devices, the velocity of dopant atoms that you are sending, that you are bombarding, that is going to be not normally distributed, yeah.
Yes, sir.
है ना? So there is no way you can have them exactly the same under every device. And you cannot model this. You can only statistically model this. So statistical models would appear, but exact models you cannot have. To do the worst case analysis, you may say that, okay, I have to assume pass gate to be at 3.5 sigma, pull down to be at 4 sigma away. And that is my worst case. That was what we did in this SNM analysis. That was what we did in the right margin analysis also in the previous lecture. So we placed devices at the worst places and we saw the impact. But it is not that this is bound to happen exactly this way. We just want to be sure that statistically we are safe.
So when you say कि statistically determined, you say कि आपने जैसे बताया कि 100 में से 70 इतना होगा, 20 का इतना होगा, but I cannot locate कि which exactly device ये variation होंगे.
Yes, that you cannot tell. 100 में से 70 होंगे, but which 70, the first 70 or somewhere randomly distributed 70, we cannot say.
ओके। और सर मतलब जैसे आपने डोपेंट का यहाँ पे एग्जांपल दिया, तो हमने वर्स्ट केस की डोपेंट भी कुछ होगा, सो उसमें भी कुछ डिवाइसेस आ रहे होंगे, बट हम
Yeah.
सारे डिवाइसेस को उस कर्व में इसी पॉइंट पे क्वालिफाई करने की कोशिश करेंगे।
No,
तो
no. That is where we did that, na? We said this is my distribution, and we said let me put pass gate at -3 sigma. Let me put pull up at +3 sigma. You remember? We did that. So we did not say कि सारे devices एक ही जगह पे हैं. We actually, for verification, for designing, we actually put devices at different corners, and that was when we did it.
राइट, आई मीन सब पास गेट का जो हमारा वर्स्ट पॉइंट होगा वहाँ पे सारे पास गेट का एनालिसिस वहीं पे करेंगे हम, मतलब सिमिलर काइंड ऑफ डिवाइसेस का।
जो भी उस सिस्टम के लिए, at times pass gate का lowest VT is what you desire. At other times pass gate का highest VT is what you desire.
ओके।
For SNM analysis, you want low VT on the pass gate. For right time analysis or right margin analysis, you need high VT on the pass gate.
यस सर।
So at time you will use one side of the curve, at another time you will use another side of the curve. Okay.
Sir.
Yes.
Sir, can you come back one slide? So sir, this according to this below graph, sir. So this dopant fluctuation is the major cause to the VTH variation.
Yes.
And sir, one thing also I want to ask, sir, at lower technology nodes, मतलब सर कम चैनल लेंथ पे, तो सर ये हम लोग का जो जैसे आपने बोला था कि जो हम लोग का सिग्मा शिफ्ट आएगा वो बढ़ता जाएगा.
Yes. That is what is shown in this curve.
Yes, sir. Okay, sir.
Okay. So again, this is about the impact it has on the memory cell. So this is actually the memory cell ka SNM analysis only, where we say that okay, for different SNM values, how is the distribution when cell ratio is moved from 2 to 3 to 4. Okay. And this has considered only the random dopant fluctuations as a part of variations as yet. Other random things are not put in picture. Another random effect is interface roughness. What does that mean? See, finally, you grow silicon dioxide, let us say. At some places, there are 3 atoms of 3 molecules of silicon dioxide. At other places, there are 4 molecules of silicon dioxide. At some places, a molecule is placed in a particular manner. At other places, the molecule is placed in a different manner. So what happens? The thickness of silicon dioxide can vary across the gate region. Some places it is 2.2 nanometer wide thick, at some places 2.6 nanometer thick, at some other places 2.4 nanometers thick. So what does this mean? That even though you said that your gate is 22 nanometer thick or 25 nanometer thick, there are variations around it. The gate oxide thickness is not exactly the same. Due to this, some devices will operate fast, some devices will operate slow. Adjacent devices both have average thickness of 25 nanometer only, 25 angstroms only. But in one device, it was more towards 24. In the other device, it was more towards 26. And it is random. You cannot control it. Are you with me?
Yes, sir.
So this again is a random variation which you have to model in your Monte Carlo simulations. Another random variation is line edge roughness. What does line edge roughness mean? Line edge roughness means that you wanted to design a poly which is of one particular width throughout. Whereas poly in itself is a is a polycrystalline material. So there are crystals there. And when you will do etching, when you will do chemical etching or anything, you remember that crystals have anisotropic behavior. They behave differently across different directions. So there is a crystal which is placed here and a crystal which is placed here. So when you do the etching, what happens? So let us take this example. Let us say that there are these different crystals of silicon dioxide that form the poly region over here. And so on. So when you started to etch, what happens? The crystal boundaries, at the crystal boundaries, the extent of etch changes. So finally, you may have a polysilicon line. So you wanted it to be completely straight and parallel. Finally, you will have a polysilicon line, which could be like this. Thicker somewhere, thin somewhere, and so on. You notice in this image, the poly thickness is not constant throughout. What does this mean? This means that the length, effective length, is changing. Now let us say there was a contact over here, and in another device there was a contact over here. The effective thickness of the gate for transmission of current from source to drain, from one contact to the other, is going to be different for every device. Are you able to see this?
Sir? Sir, how is the thickness changing? I mean, along the line it is changing, na? So thickness so remains will same, right?
So
it is along the edge.
Thickness, I mean, okay, let me not use the word thickness. Let us use the word width. The length of your device is changing. Are you able to see this? Now, the length of the device is changing differently for different devices because of this line edge roughness.
Also, sir, it seems that in the same device, the length is not constant throughout.
That is also the case. But there will be average length. So average length may still be 65 nanometers, let us say. Okay, average length is 65 nanometers, but because of line edge roughness effect, the current flow which was happening from one contact to the other, the effective gate oxide thickness would be different. The effective poly length, the gate length would be different. There will be variations there.
Sir, it is written that LER is independent of gate length. So, yes. Sir, how it is causing variation, sir?
LER is independent of gate length, but it does not say that LER doesn't happen.
Yes, sir.
If LER is happening, do you realize that gate length is effectively changing?
Yes, sir. Yes, sir.
What it means that it is independent of gate length means that it is dependent on polycrystalline, the size of your crystals in the polysilicon, not on the length of your gate. Whether it is 1 micron wide length or it is 65 nanometer length, yes. The variation will always be plus minus 3 nanometers. Okay, that is what it means by this statement. It is not a percentage variation.
Sir, if it is dependent on the crystalline this thing, so sir, if with the same crystal we are manufacturing 65 nanometer, and then we are moving down lower technology nodes. So sir, this thing will be constant, na? This LER in every technology node.
LER will be constant, but let us say there was a 65 nanometer technology. Because of this plus minus 3, what is the fastest or what is the minimum length that you will get? 62?
Yes, sir.
62 versus 65, what is the percentage difference?
Uh,
Something like 5%.
yes, sir.
Now let us come to 20 nanometer technology.
Then it will cause, yes, at lower technology node, then it will be significant.
The impact is much more.
Yes, sir.
The
Okay.
difference is now around 15%.
Means, sir, this LER will be same across every the channel length, but it will be more significant in lower technology nodes.
Not just lower technology nodes, in the same technology node, if you use minimum length, the impact is more.
Yes, sir. Yes.
Why lower technology? Lower technology node is a different technology. You actually use a different material.
Yes,
You
sir.
could use a finer, more granular polysilicon.
So, sir, for removing this crystals, we can use, sir, we can be more precise during making these. So we can use lower wavelengths to manufacture. So we can avoid this LER.
Do you use wavelengths to manufacture?
Sorry, sir. Sir, we studied that in that, sir, sir, that optical OPE, sir.
So do you remove it through OPC?
No, sir, but we can avoid.
How does removal of how does removal happen finally?
No, sir, removal. We can avoid this polycrystals, sir. So that we may avoid LER, sir.
So you will not use polysilicon then. What will you use?
So, सर जैसे कि सर उसको अवॉइड नहीं कर सकते हैं क्या जो क्रिस्टल
आप बताओ ना, आपने, मैं आपका आइडिया सुनना चाह रहा हूँ रजनीश, आप क्या कह रहे हो, मेरे को समझ में नहीं आया.
Sir, I was just asking, sir, if we could avoid this, sir, extra जो rough edges आ रहे हैं, sir, इनको अगर किसी तरह हम लोग avoid कर लें, sir, तो सर जो हम लोग का
देखो ये तो इच्छा मेरी भी है, सॉल्यूशन बताओ ना.
सॉल्यूशन सर हम लोग मतलब कोई लोअर वेवलेंथ यूज करें ताकि हम लोग का सर कम से कम ये एज रफनेस है.
तो वेवलेंथ से क्या होगा? मैं कैसे रिमूव करता हूँ इसको, पॉलीसिलिकन को? मैं एक मास्क बनाता हूँ, मैं उस मास्क को लाइट से इंजेक्ट करके हार्डन कर देता हूँ. अब रिमूव करने के लिए मैं क्या करता हूँ? मैं एसिड डालता हूँ. आई पुट एसिड देयर.
यस सर.
दैट एसिड रिएक्ट्स विद पॉलीसिलिकन व्हिच इज एक्सपोज्ड and I wash it away.
Yes.
Now, where does light come in here? There's a chemical reaction that is happening.
Yes, here it's not needed. Yes. Okay,
there's a chemical reaction that is happening, and that chemical reaction is anisotropic in nature because of the crystalline structure.
Okay, sir.
It's a physical process. It's a chemical process.
Yes, sir.
Hello?
Okay, sir. Yes.
Okay.
Sir, the mask which you make, that will be making it with the help of the light, right? I think that's what he was mentioning before.
Yeah, and that is what I'm clarifying. It is not about the mask at all.
So if
it is about the process. It is about the process of etching. It is about the chemical removal of the polysilicon that was extra there, so that only polysilicon wires remain. It is about that.
Yes, yes. Okay.
That is what I'm clarifying.
So the graph on the left, sir, the x-axis, what is signifying, sir?
The graph on the left.
Right, sir. Sorry, right. The below graph. The edge
it
deviation.
It is just saying that as you move away from, as you move from one part of the chip to another, the edge, this variation is simply varying. There is no constant, there is no, what do you say, there is no pattern there.
Yeah.
Is there a pattern? No, there is no pattern. Some places there is more roughness, some places there is less roughness. It is just how polysilicon got deposited.
Yes, sir.
Okay. So now this is what we just discussed. Even if the variations remain constant, even if the line is, delta L, we said is constant, you see the impact across technologies is very different. That is why as we go to still advanced technologies, more and more variations are coming into picture, and they impact memory design very, very significantly. Okay.
Sir,
Yes.
sir, actually here only in the first slide also I had this question. Sir, here it is written that we in the random variations we had three kind of variations, right? But here it is saying that the intrinsic random variations tend to be constant magnitude. So what exactly do you mean by the intrinsic random variations? I mean,
This
that I wanted to
lineage
know.
roughness. Lineage roughness is intrinsic to the way device is manufactured. Interface roughness is intrinsic to the way silicon dioxide is deposited.
Okay.
They are intrinsic. They are not because of something else. Two polys are placed right next to each other. It is not one poly. So this device, the dopants that will come under one gate is not dependent on any other gate. Is it dependent? Whether I placed another gate close to it or far away from it, is it dependent on that? No. Therefore, it is called intrinsic variation. Well proximity effects and others could be considered as extrinsic variations. That poly necking and everything, they are extrinsic variations.
And so in the random variations, there was also one subcategory of pseudo. So how is it
Pseudo
different from
was,
that?
pseudo is something like you have two devices, but there is a temperature gradient because of some heat being generated in some place. Now there is a temperature gradient. Physically, the devices were similar, but now due to higher temperature in one cell, in one device and lower in the other, the mobility has changed a bit.
Okay.
There is some
So
IR drop that happened, let us say. So everything was same, but due to 20 millivolt IR drop, now the VGS that you observe is little different. Those are pseudo variations. Again, you cannot
okay,
say
like
what will happen. They are dependent on some patterns, how you will run the device, how the user will activate the device, and so on. Okay. So now
sir,
this, yes.
so sir, like in intrinsic, we are only taking consideration the device and the process. I mean, nothing else is there. But in the pseudo, we are considering apart from the device, some external event. I mean.
Yeah, which we do not have control over.
Okay. Okay, sir. Thank you, sir.
Okay. Now, in terms of VT variations, there are multiple reasons why VT variations could happen. We talked about dopants, we talked about interface roughness, we talked about line edge roughness, and so on. But there are other variations also, that there could be band gap variation, there could be work function variation, and so on. And all of that could be because of different reasons. Well proximity effects, so some are systematic, some are not systematic, and they all have to be modeled into your device equations, so that when you run Monte Carlo simulations at your end, you're able to see impact of all of them collectively on your circuit behavior. Okay. As I mentioned, we will share the entire big slides with you. You can study them in detail. But this was just to give you a glimpse of various kinds of variations that happen. Then, as Raghav was just asking, there are some variations which are environmental in nature. For example, supply voltage fluctuations could happen, temperature could change. And there are some variations which are operational in nature. For example, clock jitter. And static and dynamic variations in terms of IR drop, junction temperature, and all those things across the chip. So when we say environmental variation means you decided to run the chip at 1.0 volts instead of 1.1 volts. That is a supply voltage variation. Okay. Or what is it? Just give me a minute. Sorry, this is jumping. Or there could be clock jitter, which is happening on the fly. Okay, so these are pseudo. So these are the clock jitter and everything. These are pseudo variations, pseudo random variations. Okay, they are not intrinsic. They are pseudo random, but they are there. They may happen at some time. They may not happen at some time. Therefore, they are dynamic. You cannot always assume them to be there. But these environmental variations, so you can actually simulate at 1.0 volt and see the impact, or 1.1 volt and see the impact of it on your system. So these environmental variations are a part of your PVT condition. The operational variations are something that you need to leave margins for. Okay. So again, as I said, some of the variations can be modeled, some cannot be modeled. And whatever it is, you have to operate your design accordingly. You want to model as much as possible. At times, you model the exact variation. At times, you model the variation in a statistical manner. So then you will need to run the Monte Carlo simulations to verify your circuit. Okay. And yeah, this is a quick summary that there are different kinds of variations and there are ways to handle them. You can make structurally good layouts. You can make matched layouts so that at least systematic variations are minimized. But there are some variations which will normally always remain. To handle them, you can use larger devices, larger width, larger length, so that the impact of those variations is reduced. The more the gate area of your device, the lesser is the impact of random variations on the device. Okay, so for the sense amplifier, when you design the sense amplifier, you will not use minimum length devices if you want to reduce the random variations. For the memory cell, we do not use the minimum length devices. Two reasons: we want to reduce the leakage, but also because the variation impact can be very, very significant if you use minimum length devices. Okay.
Sir, sir, you can explain this DFM thing, sir?
DFM means design for manufacturability. We saw that there were variations. You remember the systematic variation slide that the second slide that we saw, जहाँ पे necking हो रही थी, there were bends in the poly and everything.
Yes, sir.
Some contact pads were bigger, some contact pads were lesser, and so on.
Okay.
Now, this led to variations in poly width.
Yes, sir.
We know that this is systematic variation. If such
Yes.
systematic variations can lead to yield loss, then the technology teams will give you an additional set of rules which are called as DFM rules, design for manufacturability rules. What this means is that if you have sufficient space in that region, please give that extra spacing. Please keep only parallel polys. Do not bend the poly here and there. So for example, in 45 nanometer, there is a DFM rule which says do not give bends on poly. In 32 nanometer, we said no bends on poly are allowed at all. So a rule of an advanced technology could still be followed in an older technology so that variations are reduced, and that is called as design for manufacturability.
सर मतलब कि वेरिएशन से बचने के लिए हम लोग एक एक्स्ट्रा सेट ऑफ रूल्स फॉलो करेंगे.
Yes.
पर सर इससे सर हम लोग का एरिया कॉम्प्रोमाइज इसमें भी हो जाएगा.
नहीं, तो इसलिए मैंने कहा अगर स्पेस है तब.
Okay, sir.
So that area loss ना हो.
Okay, sir.
And this can be done if you design with the DFM already in mind. You can actually make very good dense layouts. No area penalty, but very dense layouts, and you can make them.
Okay, sir. Yes.
Okay. So I will post the entire, tutorial in the classroom. I would strongly recommend that you study the tutorial in completeness. But in this lecture, I kind of have introduced you to the most important sources of variations and what to do about them. But there is much more. The entire tutorial is very, very big. I've just picked up a few slides over here. So I would strongly recommend that you see the full tutorial. Raghav?
Sir, can you move 1-2 slides before? I had so in which there was a table, comprehensive table, I mean, before that. So before this, I mean, before this also. Yes, sir. So I mean, for example, the first row that I'm seeing, so you have sent the doping profile, right? And there we could various causes, and then you have the variables put there. But I can see that you have all the kind of dopant. If for example, certain fluctuations or variations are happening due to the dopant profile, you will be modeling them as VT variation, right?
Yes.
That you're saying. So, but on the variable side, you have included the well proximity effect. That is a structural thing. and the dopant fluctuation, that is interesting thing. So I mean, you are
No,
modeling
no,
the
no, no, no.
random and the
So,
structure are same VT.
no, no, not same VT. What we are saying is when we decide the VT, we have to be some variable of well proximity effect also coming in, some variable of random dopant fluctuations also coming in, and so on. So you will see that when you will extract layouts in advanced technologies, there will be a lot of extra variables that will be. So abhi aap jab 65 mein dekhte ho, when you extract a device in 65 nanometer, what do you see? You see W, L, PD, PS, AD, AS, and that is the kind of place where the variables end. Am I right? In advanced technologies, you will see there is another variable called A. There's another variable called PO2 act. There's another variable called something else. What does that mean? We are adding variables, additional variables in my extracted netlist so that I can model the well proximity effect into devices which are susceptible to it. I can model stress effect wherever it is relevant. You notice dopant fluctuation has been in brackets mentioned as intrinsic. So you cannot model it through extraction. What do? You model it in statistical simulations through Monte Carlo. You see, it is mentioned as intrinsic over here.
So सर लाइक आई मीन अगर मैं एक लाइक वीटी की इक्वेशन मान लीजिए मैंने एक वीटी की इक्वेशन लिखता हूँ तो उसमें जो बेल प्रॉक्सिमिटी है डिस्टेंस इन सब के कांस्टेंट टर्म्स आ सकते हैं बेसिकली
but which are multiplied, so there will be some effect which will be multiplied with the value of well proximity or distance from the well as recorded in your extracted netlist.
ओके उनके कोफिशिएंट्स कुछ बन जाएंगे जिससे मैं कर पाऊंगा
yes
ओके सर एक और चीज थी सर जैसे बोलते हैं ना एक्चुअली ये चीज तो मेरे क्लियर नहीं होती कि व्हाट डू मीन बोलते हैं ना कि स्टैटिस्टिकल मॉडलिंग करते हैं वो चीज मतलब सर क्या मतलब बोल रहे हैं आप
you've done Monte Carlo simulations, ना?
यस सर
What do Monte Carlo simulations do?
सर मतलब गॉसियन कर्व में हमें बताया था कि
What is a Gaussian curve?
सर मतलब कि हमें we have a bell shaped curve in which you have a sigma and a mean value and we say that कि most of the devices will be lying at the mean value but sigma after this sigma certain device will be on this side or that side वैसे करके मतलब
So that is statistical modeling where you're saying 70% of the devices will be within plus minus sigma. Another 25% of devices are within plus minus 2 sigma. Another 3% of devices are within plus minus 3 sigma. That is statistical modeling.
Okay, sir. उसी को हम statistical modeling बोल रहे हैं सर.
That is about statistics. Now, how many devices are within this range? We discussed now. Because we were talking about exactly the same thing.
Okay, sir. Yeah.
Yes, So statistical modeling means that you define how the statistics would be. You cannot define this as okay for well proximity effect. You got a variable in your extracted netlist. You simply multiplied and you knew what the VT change was. But for dopant fluctuations, you cannot do that. You can simply say the statistics linked to dopant fluctuation and then you run Monte Carlo. Done.
Yes, sir.
Okay.
Got it, sir.
Yeah.
Thank you, sir.
Okay, guys, all the best. And the TAs will open up the sheet so that you can start to discuss the projects and zero in on the projects of your choice. And then they will be opened up for registering. Okay, so you can put your names after that. All the best.